In this video, we're going to do a brief introduction into sets and set theory. So we start with the definition. So a set, we say, is just a collection of objects. The objects within the set we call elements. And the best analogy I usually use is to think of a set as a bag of things. So the things inside the bag are the elements, and the set itself is the bag. So some properties we usually demand for sets. The elements inside can be anything. Okay, so this includes letters, numbers, colors, places. They could also be other sets within a set. That's fine as well. We don't want any repeated elements in the set. And the order we write them doesn't matter. So a set often is described by listing the elements using curly brackets. So those are these kind of brackets. And you can also describe the elements explicitly instead of listing them in a couple of ways. So let's just do a few examples here. So maybe A has some letters in it. So maybe it's the set AB. So it contains the letters A and B. Note that this would be exactly the same set if I wrote the letters B and then A, because they have the same elements. It's the same set. Okay, the order doesn't matter. Maybe B is a bit of a weirder set. Maybe it has types of animals in it. So I have a dog, a cat, maybe a bird, maybe a fish. Okay, so perhaps we want a set with some animal types in there. Let's do set C. I'm going to write it a bit differently. So C is all the x's such that, so that's how we read this vertical line, which I'll write after. X is a vowel in the English alphabet. Okay, so when you see these type of vertical lines, you read it as such that. Okay, so that means that what C looks like would be the set. So because there's not too many elements, we could actually list them out. So C would be the set containing the letters A, E, I, O, and U. Okay, let me just write this notation that I used is called set builder notation. Okay, so some notes. Like I did in these examples, we usually use capital letters to denote the set, so the set name. Lowercase letters if there's letter elements inside. We also use this notation here, so that's little a, so an element, a random element. This sort of weird looking E is in, or is an element of, is how you could read that. So this statement here says A is an element of the set capital A. Okay, now if there's a slash through it, like there is here, obviously that means A is not an element of capital A. So some ways to combine sets, so that's often how we want to work with them. So the two main ones are union and intersection. So if you have two sets, A and B, and you want to combine them using a union, we use this notation. So that's A with like a capital U looking symbol, and then B, you read that as A union B. It would be defined as the set that contains elements, okay, so all elements in A, in set A, or in set B, okay, or possibly both. So in math, when we say or, we always mean one or the other or both. So this is an inclusive or. If we wanted the exclusive or, oops, I missed a word here. If we wanted the exclusive or, then we would specifically say and not both. Okay, so if you see the word or, this is what you should assume, unless it says otherwise. The intersection is a bit more intuitive. So if you have two sets A and B and you want the intersection of the two, so we use this symbol here. So the union symbol just flipped upside down, and we read that as A intersect B or A intersection B. This is defined as the set containing all elements that are in A and in B. Okay, so these are the common elements that they have in common. Okay, so when you're thinking about union and intersection, for the union, you want to think of the word or. Okay, for the intersection, you want to think of the word and. So just keep that in mind when we're doing the examples. Okay, let's try one out. So let's say A is the set containing the numbers 1, 2, 3, and 4. B is the set containing the numbers 2, 4, and 6. We want A intersection B and A union B. So let's start with the intersection. It tends to be easier for people. So A intersect B is the set, so I use the curly braces. And what I want to do is look in A and B for numbers they have in common. Okay, so I see that they both have the number 2 and they both have the number 4. Okay, so in my intersection, the set is going to include just the numbers 2 and 4. So that's what they had in common. When you're doing a union, so A union B, this set is going to have all the elements that are in A or B or both. So another way to say that is it's going to have all the elements that are in at least one of A or B. Okay, so the way that I usually write the unions is I just pick a set, so let's say A, and I write down all of its elements, because being in A is enough to get you in the union. So these are from A. And then what I do is I look at B. Okay, I don't want to write any repeated elements, so I don't want to write 2 and 4 again. But if B has anything extra, I want to add it in. So here there's an extra 6. So I add that in the set, and that's all that's in either of them. So this is extra in set B. So that's how I normally do the unions. Okay, now an example where the sets are not listed out explicitly. So A is the set of all types of mammals. Okay, and B is the set of all types of animals that lay eggs. Okay, there's a nice picture over here. Obviously we haven't talked about Venn diagrams, but you probably have some intuition as to how they work. If not, though, we'll talk about them later. So we want to intersect and union these together. Okay, so again, we can't list, well actually for the first one we could, but we're not in biology, so we don't need to know which animals are both. But that's exactly what would go into set A intersection B. So you have to be in A, so you have to be a mammal, and you have to be in B, so you have to lay eggs. Okay, so in A intersection B, it's the set containing all types of mammals that lay eggs. Okay, so just to be sort of explicit here, being a mammal is what gets you in set A, and laying eggs is what gets you in set B. So if you do both, you're in both sets. Now as a side note, there are mammals that lay eggs. These are called monotremes. Okay, you don't have to know this, but there's 6 of them, and in the middle here is a platypus, is one of them. So there are some types in there. The union here is going to be, so you have to be an A, you have to be an A or B or both. So this is going to include all types of animals. Oops. That are mammals maybe I should say creatures, but okay, all types of animals that are mammals or lay eggs. Okay, now we don't need the statement or both because obviously or means that, but I'll write it here just to be explicit. So everything in A set will be in there, everything in the B set will also be in there. You can extend these to more than one set. So if you wanted A intersection B intersection C for 3 sets, the elements that would be in there are elements common to all of A, B, and C. So it would be elements that they all have in common. The union, A, union B, union C, would be elements, so all the elements in at least one of sets A, B, or C. Okay, so being in 1 is enough to get you in the union. You could be in 2, you could be in all 3. You're still going to be in the union. Now be careful, it's important here that these symbols are both the same. Okay, if they're different, then the order that you do them matters. So here they're the same, so we don't have to worry about that. A special set that we often encounter is called the empty set. So we usually denote it with a 0 with a line through it, although you could also denote it with 2 empty curly brackets, because what it is it's the set with no elements. Okay, so it doesn't have anything, it's an empty bag. Okay, so it's a set, so it has a bag, but there's no elements in it. Now my warning to you is to be careful, because this, the empty set, the 0 with the line through it, is not the same as the curly brackets with the 0 through the line through it. Okay, so to try and illustrate this, the left side is just an empty bag, whereas the right side is a bag containing an empty bag. So remember I said that the elements in the set could be other sets. So an empty set could be an element of another set. Okay, so you want to be careful about that. We say that 2 sets A and B are disjoint if they have no elements in common. Okay, so another way to say that would be that their intersection is the empty set. Okay, so that means they have nothing in common. We can also make more sets from a set A by selecting only some of its elements. Okay, these sets are called subsets of A. So set B is a subset of set A, and we write it using this notation here, where it's like a less than or equal sign, except it's rounded, and you would read that as B is a subset, of A. So this would happen when all elements of B, so of the subset, are also elements of A. Okay, so A could have more elements, but all the ones in B are also in A. Then B would be a subset. So if we have the set A containing the letters A, B, and C, let's list all of the subsets. So for your first instinct, we can only use elements from A. Okay, so the set containing only A is a subset. The set containing the letter only B and only C, so all these one element subsets are all subsets. We could also have 2 elements, so the set containing A and B, the set containing A and C, and the set containing B and C. And the 2 that people often forget, you could actually have all the same elements. Okay, so A is actually a subset of itself. And in fact, the empty set is a subset of every set. Okay, so the empty set is also a subset because it doesn't have any elements. So sort of immediately, all of its elements are also elements of the set because there are none. The universal set is another special set. Normally in examples, it's given or sort of obvious by context. But it basically is the overarching set where all the other sets in your example are subsets of this set. Now we need the universe in order to define this last operation that's called complement. Okay, so the complement of set A which we denote here as A with an apostrophe, so you read that as A complement. It's defined to be the set that contains elements, so all the elements in the universal set U that are not in set A. Okay, so it's everything opposite from A. Just a side note here. So if you intersect A and A complement, obviously they're going to have nothing in common, so you get the empty set. Because set A complement has only things that are not in set A, so they should not have anything in common. If you union them, then you should get everything, so the universal set, because every element has to be either in A or not in A, and therefore in A complement. Okay, one more example. So let's let the universe here be the letters A, B, C, D, E, and A has the vowels A and E, B has the letters B, A, and D. So we first want to find B complement. Okay, so this is the elements that are in U that are not in B. So what we want to do is get rid of the elements that are in B. So that's B, A, and D. So the complement is just going to have the letters C and E left over. Okay, now the next one, we want the complement of the intersection A intersect B. Sometimes I think it's handy to do some steps here. So I'm going to compute A intersect B on its own. So what do A and B have in common? Well, they just have the letter A. Okay, so that the intersect is just A. So the complement of that is going to be everything other than A. So we're going to have B, C, D, and E in that set. Okay, now lastly, we want to compute A complement union B complement. So again, we already have B complement, but maybe we want to write out what A complement is so we know what we're working with. So it's everything in U that's not in A. So it's going to be B, C, and D. Now we want to union these together. So I can start by writing A complement, B, C, and D. Okay, so these are the ones in A complement. And now I want all the extra ones in B complement, so I already have C, but I don't have E. Okay, so those, that would be A complement union B complement. Now you might notice that these two are actually the same set. Okay, this is actually not a coincidence. This is an example of a fact that's always true called De Morgan's laws. So if A and B are sets in some universe U, then the complement of A intersection B, the one we just did, to compute it, you could instead compute the complements of A and B, but you put them together with the opposite symbol. Okay, so we were trying to complement an intersection, so instead we union the complements. Similarly, if we want to complement the union, we could complement each set individually, but then we intersect them. Okay, so these are called De Morgan's laws. They can be useful sometimes to use. Sometimes it's easier to compute one than the other. So that's our very brief introduction to set theory. Thanks for listening.